So, okay, so today I'm going to switch to another topic, and all the topics are going to come together as building blocks to what we're going for. Again, it's an introductory class, so we cannot, we're not concentrating on one thing, but we're getting building blocks. Okay, so today we're going to concentrate on the detectors. Up to now we're able to figure out the units and estimate things, and the main things in high energy physics, you calculate cross-section and interaction rates. The point is to know if you're looking for new physics or measuring existing physics or calculating existing physics is usually cross-section or decay rate or lifetime. Now, detector is not a word that's unfamiliar to you. This technology has been for a while. Not only for a while, it's been used by many different research in science, and you can see, for example, the structure determination via X-ray. We're using diffraction in biology and chemistry, airport scanners, detection of explosive. Another one is PET scans, which is very interesting. Actually, I looked at PET scan yesterday because I forgot how it works, and it's actually neat. It's like, so I remember, what was it? It was it's proton tomography. What, emission tomography? Yeah, proton emission tomography. Yeah, so it's E plus E minus, exactly. So it's E plus E minus coming in, and 2 photons coming out, and you basically, everything is working thanks to a tracer that you drink, and it's a sugary tracer, and it goes to areas where the cells, require this energy. So usually, God forbid, areas with unwanted, problem like cancer or stuff like that, I guess require more sugar, and then they have these unstable atoms in them that decay, and it creates this indirectly, this E plus E minus that decays to photons, and that's what you're actually recording, this emission of the photons. So obviously this is used in many different areas. And now the question is particle physics. Why physicists are why are we using detectors? What are we trying to do? So one of the main things is physicists are trying to solve main puzzles of nature. For example, what's the origin of mass? Like I discussed it in the first lecture, that we keep measuring different and finding particles and their masses, but we don't understand why the hierarchy is the way it is. Why matter is made of fermion and forces are carried by boson, why the main interactions are so different and in different strengths. Gravity is not included in the big picture of the theory yet. It's like, we didn't even measure graviton yet, only gravitational waves. So we never saw a graviton. What could be the dark matter that keeps together the galaxy? How many are really the dimension of our world? And the hope was they will build this LHC and everything will be kind of starting to be explode in this TeV region. That looks funny. Okay, so the standard model that we are going to discuss a little bit more is basically one of the most successful theories, and the accuracy of the measurements and the theoretical are even better, is 10 to the minus 4, depending what measurement. We have LEP, we have CDF, different accelerator detectors that were built, the different accelerator, and the idea is the one that we're up to now, we're measuring physics until the 100 GeV. And then LHC was supposed to deal with an order higher of 7 TeV. And one of the questions that I mentioned is why the masses are so different. And so matter particles range from 0, almost, like neutrinos are almost 0 GeV. And we're going to up to 170 where we're going to the top quark. So we really have a long range of masses. And while the forces are ranging from 0, the mass of the photon, to 90, which is 91, which is the mass of the Z boson. So we have like totally different range of masses. At energies that are much higher than 1 TeV, we see the probability of scattering of one of these W boson of another become much bigger than 1. So if I looked at this cross-section, I would find out that the amplitude for this one, where W collide against another W and create two Z's, the amplitude, the probability of the scattering is proportional to the amplitude square, and that is bigger than 1. So you know if an amplitude is bigger than 1, I mean probability bigger than 1, I mean it's not physical. Probability has to be less than 1. So one way to fix it was to actually introduce the Higgs boson. That was another interesting idea why the Higgs boson is a good theoretical candidate to be there. So it's a popular solution that was to introduce the Higgs. And the exchange of that Higgs between the two, so you will have to calculate the cross-section, you will have to add the two probabilities because it can go through this or through that, right? What you see here is like two W's coming in, two Z going out, but it can go through a T channel that I discussed last time or a S channel. So, but the T channel will go with a W and the S channel through a Higgs. So that was introducing a new particle called the Higgs. And we find out that if we do that, the amplitude, the general probability is less than 1. So that was like an interesting way of solving this problem. So that will bring a theoretical limit on the Higgs. Putting all the limits together made the Higgs to be somewhere between 100 to a TeV, and everybody was looking for it. And another interesting thing about the Higgs back then was that if the Higgs is light, quantum radiative correction to the Higgs boson mass. So every time you calculate something, you can also calculate the mass of the particle. And everything comes with correction. So when you calculate the mass, you have correction to it. And it turns out that if there was a theory called supersymmetry, which I mentioned before, that introduced like a symmetry between fermion and boson, for example, and it introduced minimal supersymmetry has new particles called neutralinos, charginos, a bigger Higgs sector, etc. All this would be introducing. You will basically have a way to actually make. Actually, what did I want here? If the Higgs mass is light, there are different scenarios that actually support it. One is minimal supersymmetry. One is called R-particle conservation, and all these little theories I will discuss at the end were kind of highlights of what these theories are. And in addition, there's something called GATT unification that will be good at the TeV here. So it turns out like one of the beautiful things that supersymmetry was adding to the Oz picture, it would have been that like unification of the forces would have been like at the TeV scale. So that was another kind of justification to kind of hope that there is supersymmetry. So this is kind of different idea that like people were hoping why we want to go to build another accelerator. There's so more questions that we don't know and we want to solve. For example, here in LHC, people were talking not only to look for supersymmetry, actually looking for supersymmetry. In this picture, what you see is the motion of the stars in galaxy, and you can look at the rotation curves. So we have here the rotational velocity versus the distance from the nucleus. You can see here, and we're talking about galaxies here. And you can see when they measure, and you measure this with Doppler, right? Yeah, Doppler shift, like light shifted to the blue is when the galaxies are moving towards us, and it shifted to the red when they're moving away from us. So you can measure the speed, the velocity of these galaxies. And you can see that when you're within this radius where there's lots of galaxies, it goes like in simple mechanics, the velocities linear. And what you would expect is that away from the area there's lots of galaxies, then the speed with the velocity will go like 1 over square root of r. So it should go down here. And what we see that it doesn't happen. So the fact that it doesn't happen, what it means is that there is some matter here that I don't know about it, and that's what I call like dark matter. And this dark matter is what contributes. So that's why the speed, the velocity of these galaxies away is staying straight, stable, instead of like going down as 1 over square root of r. Yeah?
That is the velocity of the galaxy?
Yes. Yeah.
In terms of the velocity, yes. In terms of...
Versus the distance from the center. So you look from the center of the cluster of galaxy, like center of our galaxy, and you look away like and you see that as you go there's lots of galaxy going around. It's very like there's a certain density of these galaxies, and you calculate the velocity and you see that okay, the velocity is going like proportion is linear, like it should be. But once the density of this galaxy is smaller, of the stars is smaller, then you expect that like it will go to 1 over square root of r, but it doesn't. It's straight. That means there's dark matter, and one of the hypotheses for dark matter is having neutralinos, weakly interacting massive particle. And so that was another motivation that people were hoping in the next accelerator we will see it. Here we can see that when they're planning LHC, for example, and talking about the Higgs boson, they're saying what energy should I give to this proton beam. And you can do like back of the envelope estimate. You say if I want to be able to measure a Higgs at a 1 TeV, that means the energy of the W, each one of them should be bigger than 500, and therefore the energy here should be more than 1,000 GeV, and since I have like quark and gluon here, it should be bigger than 6 TeV. So they talked about giving 7 TeV to each proton beam to be able to produce a Higgs up to 500 GeV, something like that. So that's the idea of like, what do I do next, and what am I trying to do? When you think about what do I do next, I need to know what question I'm trying to solve, what energy I'm going to be able to deal with, what is the minimum energy to make this physics worthwhile and interesting, otherwise nobody will give you the money. And you can see here that the cross-section for various physics processes vary over many orders of magnitude. So to produce a Higgs at 100 GeV, I need about 10 picobarn. And to produce, so 10 picobarn or 1 picobarn for 600 GeV Higgs means that if I have a luminosity, which is the interaction rate, which is 10 to the 34 inverse centimeter square inverse second, which means it's 10 to the 10 inverse bar or 10 to the 7 inverse millibar. So that, actually I want millibar, I want picobar. Anyway, so if I multiply, this is 10 to the 12, 10 to the, this is 10 to the minus 11 times 10 to the 24, 10. Okay, this is 10 to the 10, this is 10 to the minus 11, I get 0.1 hertz. So I have 0.1 hertz. This is the rate of interesting physics to come in. So I produce, remember that the collision rate will be 40 megahertz. And out of this, only 0.1 hertz will be interesting. So most of the stuff is not interesting to us. You see, like the inelastic scattering, which is not interesting at all almost anymore because it's well known, is at a huge rate compared to what's interesting. So I have to get rid of it. So the selection is 1 to 10 to the 10 to the 11. So that's quite of a challenge when you have to kind of consider of building a new detector and a new accelerator. What energy do I want to do? What are the requirements from the detector? So CDF and D0 were at Fermilab in Chicago here, and they successfully found the top quark facing very similar rejection factors. So similarly here we can see physics signal at, you can see how the physics signal are extremely, the interesting one, are extremely low. So this is how many events per year I'm expecting. So this is so much physics and so much work, and in the end it's like, how do you say, this is to get a needle in a hay of hay of stack? Oh, it is? Oh yeah, because it's really like that. Because it's like really getting 1 or 10 events after a year. It's really a lot of work. And then would somebody believe you when you see few events that this is really the events? So remember, you have to deal with biases and fake events and electronic that faked your signal, and everything has to go right, and you have to convince everyone that I cleaned everything, I know what I'm doing, and that's a real event. So you can see here the PP cross-section and minimum bias events. The rate here at the edge here is measured from cosmic rays. We measure this region, and we can see that the interaction rate, the luminosity at LHC at like top luminosity was like 10 to the 34. Right now they just finished the run, by the way. So 10 to the 34 inverse centimeter squared even inverse second. And the cross-section for PP collision is 80 millibarn. So if you multiply the two, the interaction rate is 8 times 10 to the 8, basically 10 to the 9 hertz. So we're talking 10 to the 9, not interesting physics, 0.1 interesting physics. So this is kind of how you think about rejection rate. And when there's a collision, you're saying like, how many, when I have two bunches of protons hitting each other, how many actually events per interaction I'm going to have, and per bunch crossing. So at this, using these numbers, you're getting about 25 events. So like instead of having one event, it's already, you have to clean it and look at it, you have like 20 events that are on top of each other, and I have to separate the event from each other, know which, because if I found a Higgs, I have to prove from which event it happened in this bunch crossing that had 25 events.